Hi everyone, my name's Amédée. I go by they, and this is Let's Run a Chess Neural Network by Hand. So why would we want to do that? And my reason is I got into chess during Queen's Gambit like everyone else, and I heard this story of a guy who wasn't a chess person, but he got the opportunity to play the world chess champion, Magnus Carlsen, and he didn't know that much chess, but he was supposed to ultra learn as fast as he could and then play and then see how it would go. But then he decided to take a different approach, and he decided that instead he was going to encode during the game. He would write down the board as a list of numbers, and then he would run a neural network, and then the neural network would tell him if his move was good or bad. And I really liked that idea. I thought that didn't really work for him. He didn't end up using that, and he still lost. But I just thought that if you did that, it's kind of a fun idea. I don't think it can work, so I looked into it. And just like in general, computers are so strong. We have supercomputers on our watches. Maybe these things that are so much better than us, maybe if we made them weaker, maybe we could meet somewhere interesting, I guess. And the answer for whether it will work or not is probably not. The way that chess engines work is that they search through this tree of every single possibility, and they search millions and millions of positions. And there's no way to do that humanly. And we've heard neural networks are everywhere and everything, and we've probably heard of AlphaZero, which briefly beats the world's best engine, Stockfish, for a little bit. But then Stockfish took the crown back and just went right back to searching that tree millions of times per second. And Stockfish did add a tiny, tiny neural network in 2020, and that helped a lot, and we're going to actually look into running that one. But even this idea that you could take the board and turn it into a list of numbers and just stare at the board once and then get the answer doesn't work, because even AlphaZero and its successor project, Leela, they don't stare at the board once. They still search something like much less, but maybe 50,000 positions per second. And until recently, we didn't even have a neural network that could look at the board once and tell you what the best move to make was. Up until earlier this year, these people in the middle published this paper saying that they had finally done that you don't need to search, and they did make this model, and if you squint, it's grandmaster level. But they didn't compare themselves to Leela, which is the successor to AlphaZero, which already said they had already done that, and they made this graph, and on the bottom it shows that this BT3 one is the same strength. The y-axis is relative strength, and it has much fewer parameters. And so right up until maybe last year, we didn't have this, and now we have one, but this has 100 million parameters, and then the top graph shows that it takes 5 billion math operations to do. So we're never going to be able to scale that down. Even if we find a bunch of tricks, we cut that down by 1,000. We're never going to do that. But that's good to know, what the ceiling is. But what if we still wanted to do it? What if we just, instead of going from the top, maybe we can just see what's the best we can do with something we can do. So we'll never be grandmasters, but how far could you go? And so I decided I would kind of set some constraints, how big would we make this? And I saw that someone had claimed to memorize 100,000 digits of pi, and so I turned that into a bytes number. And just to give an idea, in the end, the network, it fits on these 2 pieces of paper. So you could maybe memorize it, but something around this scale. So I said that I wasn't going to memorize them. I'll put them on some paper and assume that the game is really long, and so you have time to maybe take half an hour or an hour to just stop and do some math. Also, to make this a little easier, instead of playing with the network itself, we're going to have a human still kind of in the driver's seat, and they will choose some moves, and maybe they pick 2 moves, and we have the network kind of score them, and we pick that one better. But that way, the human still is in the driver's seat and is not. We're not having to depend entirely on the network. So I won't go into this, but just as a recap, neural networks have these matrix multiplications, and then they also have these activation functions that are supposed to be like neurons firing, but it turns out they don't have to be like that. There's one that's called ReLU, and it's like this. And the one we're going to use is clamp ReLU, and instead of that, it's like this. And that's it. And it turns out that that makes things really easy. And if you had to do something by hand, I would use this NNUE architecture, which stands for Efficiently Updatable Neural Network, but it's spelled backwards. And it has this killer feature that you can use it as you're going down this tree. You can evaluate it, and then you can undo a move and go back to your previous state. And so you can use this in the searching loop for your engine. It also packs a ton of really cool tricks in a tiny package. There's a lot of sparsity. It reuses weights in ways that shouldn't be possible according to the rules of chess, but it still works. Everything's integers, and it uses SIMD, which everything but the last one is also good if you were going to try and do it by hand. And when they added it, when Stockfish added it, they got these 80 points of rating, which translates to like 60%, winning 60% of the time, which for these top competitions, that's a lot. It's like the Olympics, every percent matters. So this was a big jump. I won't go into what makes it efficiently updatable, but here is kind of what it looks like. And if you're familiar with neural networks, this is actually really pretty small. And I thought I could actually even run this by hand. And it turns out because of these clamps in the right columns that are these activations, all the negative numbers become 0. And a lot of values, like 80% of the values in the later stages are all zeros. So I thought you could almost do this by hand, but then I did some napkin math and I realized it would take several hours. So I looked into ways to maybe make this a little bit smaller. You could try and train a smaller version you could quantize it. You could train a smaller version by using this one as a teacher and this one's a student. But it turns out you can use this NNUE features, which is this sparse board representation, and then this idea to combine. You run this layer twice, once from the point of view of the black player and once from the point of view of the white player, and then you combine both perspectives. And this turns out combined with like a much smaller way to represent the chessboard, and you only have one layer. This is just one output layer. This turns out to work fine, and there are people hobbyists who write their own chess engines, and they spend years crafting the way that their engine evaluates a position. So they'll say, oh, if the knights are in the middle, that's good, and the king needs breathing room, and they'll tweak that. And then they'll implement something as small as this that will run by hand even, and this will crush their handwritten evaluation that they've spent years on. And so this is so small, you can ask, like, does this actually do anything? Like, even though people who use them in their own engines, like their engines are still doing millions of positions. So to test this, I used Maya, which is another AI that's trained this time to play more like a human. So in the same way that ChatGPT is trained to predict the next word, this one's trained to predict the next move in the sequence. And you can give it different strengths to play at. And I would have one Maya play on one side, and on the other one, I would have another one generate 2 moves and play the one that this thing preferred. And I tried a few different sizes of this. And at the smallest one, this first row, you can see that if you're a weaker player, you can think of these 3 ratings as like kind of beginner, intermediate, and less intermediate. And if you're doing this and you were actually doing this, maybe you might win against your friend like 54% of it. You're winning like 4% more than you normally would. So, and then with the larger ones, is that really translates into like that translates into points. And with the larger ones, you get even like up to these 50 low points. So these are very small improvements, but I think that shows that like the number is positive and like this could work if you wanted to do it. And so here I have a video of what it looks like. The first step is there's a vector associated with every single feature. There's a vector associated with every single piece on the board and where it is. And then all of them get added together. Is it playing? Am I moving? Yeah, okay. I have to do this fast because it's really slow and really boring to do. I don't actually recommend this. It's so boring. It took like 2 hours. But there's a vector with every piece, and they all get added together. And then we can reuse that the next turn to do this incrementally, where if we want to move a piece from one place to another, we can subtract the vector associated with its old position and add the one for its new position. And that's what I'm doing here, is I'm doing all these additions. And it turns out I'm also really bad at addition. And it took a long time, even though I thought this would be pretty quick. And then the last bit is, afterwards you clamp that output. So all the negative values go to 0. That's pretty quick. And then you have to multiply these. You're just kind of combining them together with different weights. But also, all the negative values went to 0, and everything that was too big went to 127. So I decided to, in my output here, you can't see, but I had a lot of 127. So I decided to just kind of treat those first and to say maybe like 91 is 3/4 of a 127 or something. And instead of doing any multiplications, I would like add the factors, like 5 times 127 plus 2 times 127 is just 5 plus 2. And then here I'm doing you also have to do, like, there's positive ones and negative ones. And so I didn't want to do plus minus, plus minus. I just did all the positive ones on one side, and then all the negative ones, I added those together. And I have to speed this up way, way, way more, and I'm almost done. And at the end, you add these results, and you're supposed to scale this by dividing by something like, by a number to get an actual like score. But I didn't want to do the division either. And since we're doing these kind of relative numbers, we don't actually need to do that. So that's it. That's how I got this. That's running it by hand. I don't actually recommend it, but it's fun to know that you kind of could do this. And I had fun doing this in the computer. So thank you.